Hello and welcome to another video. In this video we're going to be working on path with maximum gold. And in this one you have a grid of n by n and each cell has some gold in it, or it can have 0. And you want to return the maximum amount of gold you can collect under the conditions. Every time you're located at a cell, you collect all gold in that cell. From that position you can either go left, right, up, down, you can visit the same cell more than once, and you can't visit a cell with 0 gold. So you can start and stop collecting gold from any position in the grid that has some gold. So essentially, if you actually take a look at this grid, you can see that, let's see. Oh yeah, so you can't visit the same cell more than once. Yeah, so you can't just like, you can't just like start here and then go over here and back and back and back and so on. So basically, once you go through in this picture, once you go through this middle, you can't go through it again. So you would just pick the thing that gives you the most going through the middle, and you can only go through it one time. And basically you can only get like 3 numbers total. So the biggest 3 numbers would just be this. And in the second picture, it's this path over here. And that total path will give you 28. So basically this is kind of a problem that you have to just try every single path possible, starting at every single cell. So like we'll start here and we'll say like, okay, maybe we'll go like this way, and we can't go this way because it's 0, so maybe we'll go this way. And then we can go this way, we can't because this is 0, maybe we'll try this way, and then we can go this way, maybe we'll like go down this way, and now we can't go anywhere from this way, so we'll come back, and then we'll go this way, and then maybe we'll try this way, we can't. This is out of bounds, so we'll go this way. We can't go left, we can't go anywhere else, so we go up this way, and now we have nowhere else to go. And then you would just like recurse at every single stage and see if you can go anywhere else. So this is essentially called like a backtracking DFS, where you start at a cell and you basically mark that cell visited, and then you go in every direction you can until you've explored all paths from that cell, and then you mark it not visited again. Because just because you start from a cell doesn't mean you want to like there might be a better path not starting from that cell that you need to explore. And so that's kind of the idea. So the time complexity of these kinds of algorithms is really inefficient, but the thing that's going to let this pass is, even though this is a 15 by 15 grid, like if this was a 15 by 15 grid where every cell wasn't non-zero, like if you can actually go to every cell, it would be too slow. But because there's only 25 cells containing gold, there's actually not that many paths and not that many choices. So like I'll show you kind of when we do the worst case time complexity, it'll be really big, but the realistic one will be significantly smaller. So yeah, if you try this, like if you just write this problem on your own on a 15 by 15 grid and you give it non-zero numbers, all non-zero numbers, it will probably be significantly slower. Because that would be like, instead of 25, it would be like 1 or 225 or something, which would be way too big. But that's kind of the idea. So we're just going to start every cell, and then we're basically going to DFS to other cells, and we're going to keep going. And then once we've stopped being at that cell, we need to mark it empty again, because there might be some other path to get to that cell that like starting from another cell that we haven't explored, right? Because like let's say we do all the paths starting from here, well maybe there's some better path that goes through the cell but doesn't start here that we couldn't have gotten, like let's say a path like this. So that's kind of the idea. Yeah, so I'll show you what we need for this. So let's code it. So there's a couple things we need. We need like a visited set or a visited array. We'll use visited array in Java. In Java, basically, like if you can use an array, just use an array over an object or over a dictionary. And then we also need directions. And then that's pretty much it. And then I'll kind of show you like a standard template of like doing a DFS in every direction and kind of what it looks like. This also works, I think, if you have like a graph and you're trying to find like all the paths on a graph from like some point, or just all the paths on a graph, something like that. You'd get kind of the same thing, basically. You can kind of do the same kind of thing. Okay. So the first thing we're going to need is we're going to need a visited set. So first thing actually we're going to use is the dimension. So let's just get that. Honestly, by this point, I should just like make a GitHub file or something with a bunch of these like templates for the intro stuff, because it's all the same. Then we're going to have directions, so we can call this like dirs or something. This is going to be an int array. this is going to be like this. And I believe I can do, yeah, I think I can just do like something like this. So this will be like this. So we just have every direction, left, right, up, down. So 0, 1, -1, 0, and 0, -1. We'll have a result. And then I think we want to make a few of these class variables just so we have access to a bunch of this stuff. So let's do that on the top. So we can say directions. We'll make a visited set on the top as well. So it will be an array though. So int array visited. Int rows. Let's just make all these class variables. Okay, so get rid of this, get rid of this, get rid of this. Actually, I didn't need this, but it's okay. And for our total, I guess we can leave it. Yeah. Yeah, I guess it's fine. Okay. And then we'll have some global total or something. Okay. So basically, so we do want the global total. So the other thing we're going to do to speed this up is, and this will significantly speed this up, is we're going to actually calculate the sum of the entire grid. And then when we ever get a total that's the sum of the entire grid, we can just stop there. So that's going to happen like basically if everything's connected and I start at one of the ends, then I will just have then I will just get the total of the entire grid. And the thing is, in these backtracking problems, there's like a lot of optimizations you can do, and they're going to significantly speed up this thing, because there's so many. The time complexity is so bad that one small speed up, because you're doing it a million times, is going to be a lot. Yeah. So we're going to get the total of the entire grid, and then if we ever get that total, then we know we're done and we can just return that. So let's do that, and maybe we can. I don't know if we're going to want that to be a class variable or not. Let's just make it over here. Who knows? Okay. So let's first just loop through the grid and get a total, and then we'll loop through the grid and do our DFS. So I'll do this. Rows less than rows. And the same thing for the column. So we can say this. Okay, now that we have this, now we're going to loop again and get an actual result and have a DFS. And we'll see what we need to move. Oh yeah, we need to initialize our visited set. So this should actually be, we'll just make this Boolean. But yeah, basically in all these brute force DFSs, you need rows, columns, directions, and a visited set or array or something. So visited equals new int array, and this will be rows by columns. Okay, so let's copy this code. So essentially we're gonna say our result is the maximum of our old result, or calling DFS at this row and this column, and then we're going to write down our DFS right now. And we can say if result equals, so we can say this is total gold. So if result equals total gold, then we can just return right away, because you can't do better than that. So okay. Yeah, so we just keep doing this, then we're going to return result at the bottom here. And now we need to just write our DFS function that we can just write right below this. So this will be public int DFS. It'll take an int row and an int column. So the first thing you can do in your DFS is get all the cases that are, so this should be gold. Get all the cases that are invalid. And the cases that are invalid are row out of bounds, column out of bounds, or in this case, the number can't be 0 or it can't be visited. So if it's any of those, we can just return 0 and we're done. So we can do all that. So if row is less than 0, or row equals rows, or columns is less than 0. And this is basically going to happen in all these DFSs, is your first line can just be like all the things that make it not work. So column equals columns, or grid. Oh yeah, we don't have access to the grid. We can pass that down. So grid. So let's call that on the grid. Hopefully we don't need anything else. So if grid row column equals 0, or we have access to visited because it's a class variable, so visited row column equals true. If it's any one of these, we're basically done. We just return 0. So now what we want to do is we want to have a result. So we can have an result. And we'll say that the result, and we'll make the result initialize to grid row column, right? Just the actual cell we're at. And we need to mark it visited. So when you do these like backtracking DFS functions where you're literally trying every path possible, the idea is you mark your node visited, you explore everything you can from the node, and then when you're done, you mark it unvisited again so you could visit it later from some other location. So that's what we're going to do. So here we'll have a loop that will say we should have access to the directions. So for enter a direction in directions, we're going to try to DFS in every direction. So this is maximum for old result, or this value plus DFS in that direction. So it'll be like row plus dir 0, column plus dir 1. Essentially, we'll make a move in up, left, down, right, get a result. And same thing here. So if result equals total gold, just return right away because we can't do better than that. And once we're done traversing, then like I said, what we need to do is we need to kind of do the cleanup for the backtracking. So we need to mark it unvisited again. So we need to say visited. Oh, this is going to be true. And now we make it false again. So we clean it up and we just return the result. And yeah, I think that should do it. So to sum it up, basically, you get all the directions, you get a visited set, and you try to start at every single starting location. And in your DFS, first you check, like, am I in a valid cell? If I am in a valid cell, mark it visited, do all your DFS work, and then clean it up and return your best result. So let's see if we're missing anything. Let's find out. I think we probably wrote this in the wrong place or something. Let's see. So okay, so this is in the class. So this needs to be here. And also, if that's the case, then this needs to be somewhere else as well, probably. So this is like screwed up. This needs to be here. This needs to be here. So like this, maybe. It's still like not lined up correctly, but let's see. Legal initializer. Is it like this? Or do I need to do int array first? I might need to do this way. Oh, this needs to be Boolean. Yeah. As I do like harder and harder Java things, I make a lot more mistakes. So let's see. Solution cannot be. Okay. So let's see. So this is result cannot be applied to the given types. So DFS returns an int, and this is an int as well. So do I just have this incorrect or something? Required int array, found int. Oh, it's because I'm not passing, yes, I'm not passing the grid. Okay. Okay, cool. So yeah, so if you actually do take out this like total gold thing, it's significantly slower. And there's probably other optimizations you can think of, but definitely in these in these problems, there's like in these backtracking problems, this is where optimizations like you can see the most in your actual solution runtime. Now it also does depend on the test, obviously. Like let's say there's no test that actually lets you collect all the goals, and this wouldn't help at all, and it would just be slower and so on. So not a big thing. Like it will still pass without it, but I guess we can look really quickly. So if we actually get rid of all of these, so we get rid of that, and get rid of this. Let's see what happens. Yeah, so there you go. Okay, so basically, I think we're gonna be done with this, and yeah, so let's go through the theoretical time complexity, and you'll kind of see it's too big to pass, but then because there's only 25 cells, it's fine. And that's honestly the other hard part about these backtracking problems is when you like for a lot of these problems, you try to think of, or you should be trying to think of time complexity before you even do it. So you look at the constraints, you think of a solution, you think like, okay, well, you know, if like my constraints are 1,000 by 1,000 or something, I can't have like an n cubed solution because that's too slow or whatever. And so for these, the actual theoretical time complexity is going to be too slow, but then it doesn't actually like approach that when you do it. So it gets kind of tricky because you can't really estimate it, which is kind of annoying. I think that's like the hardest part about these problems is you think it's going to be too slow, but then it works out. Okay. So basically what we're doing here is we are going through every single cell. So that part is n by m or m by n or whatever. And then in the DFS, you basically have, in every cell other than the first cell, you have 3 choices. Because like, let's say we're here, we came here from some cell every time except for the first cell. So like, let's say we start here. Like here, we actually have 4 choices, assuming they're all valid. But as you can see, like already, like even in a small grid, most of these aren't valid. But we have 4 choices in our first cell, but then let's say we choose to go here. Now in every cell after that, we can't go back to our parent, right? Like we can't go to like 5, 8, then like this loop. That's why we mark it visited. So every cell, you have 3 choices, except for the first one. So for the most part, with every cell other than the first one, and that's most of your cells, you have 3 choices. And that's basically going to be 3 to the number of cells you have, which is m by n. But really, it's more like this, because you only have 25 valid cells. And it's going to be even less than this in practice, right? Because if I do like this, if I calculate this will still get a TLE. But in reality, you don't even have this. Because like if everything was connected, there's actually not that many ways you can go. It's going to be less than this. So that's kind of the tricky thing, is like the theoretical time complexity is a lot slower than what it actually is. So space. But it's still good to think of it, and for these backtracking problems or graph problems, these are the hardest ones to actually think of these time complexities. It's kind of tricky. But this is basically, so we can call this like valid cells or something, because you can't go to invalid cells. And yeah, hopefully you can recognize now why you have 3, because, I mean, I guess maybe worst case you could write 4 technically, but like I said, for the most part in your grid, you only have 3 decisions. So maybe you can write 3, maybe you can write 4, but yeah. Anyway, so for this space, so we have a visited, which is m by n. And I think that's going to be the most of it. We obviously have a DFS. A DFS can't go like deeper nested than m by n. Yeah, it can't go deeper nested than m by n, because like, let's say every cell in the grid was a non-zero value, then that would be m by n recursive stack. So I think it's just m by n. And yeah, it's gonna be all for this one. So hopefully you liked it. Definitely kind of a tricky one, but this, you can use the same kind of thing for any problem that just asks you to get like every single path from a location. It's basically this. You just mark it visited, try to go in every direction, then clean it up. And it's very efficient, so just know that, so you can't use this for very, very big constraints. And yeah, if you did like the explanation and everything, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.